This is the 10th and final part of the Support Vector Machine series. In this video, we will look at nonlinear support vector regression. This video was produced in Korean and translated into English. My voice was generated by AI, text-to-speech. In this video, we will look at nonlinear SVR using kernel tricks. Let's implement a nonlinear SVR from scratch using CVXOPT. We will also implement this using Scikit-Learn's SVR and compare the two results. Nonlinear SVR uses kernel tricks. Kernel tricks are covered in the 5th video in this series. I recommend you watch this video first. In the Lagrange primal function for linear SVR seen in the previous video, if we replace the vector x with phi x, we get the primal function for nonlinear SVR. The subsequent process is the same as that in the linear SVR, except that phi x is used instead of x. As we did in the previous video, we differentiate this function with respect to w and b and zeta star. Then we can get the following equations. By substituting this expression for w, we can get the following dual function. The dot product of xi and xj in the dual function in linear SVR has been replaced by the dot product of phi xi and phi xj in nonlinear SVR. And the constraints of this dual problem are as follows. These constraints are the same as for linear SVR. The first constraint comes from this equation. And in this equation, c and eta are both greater than or equal to 0. So lambda is less than or equal to c. Likewise, in this equation, lambda star is also less than or equal to c. These become the constraints of the dual function. Therefore, the dual function becomes an optimization problem with one equality constraint and 4 inequality constraints. Quadratic programming allows us to find the lambda and lambda stars that maximize the dual function. In linear SVR, we could find w from this equation using lambda star and x. However, in nonlinear SVR, even if we know the lambda and lambda star, we cannot find w in this way, because we do not know phi x. Multiplying both sides of this equation by phi x gives us the following equation. As we saw in the support vector classification, we can use the kernel function to find the dot product of phi xi and phi x. So we can find the dot product of w and phi x. Then we can find b from this equation. This is an equation where x in this equation is replaced by phi x. Now that we know the dot product of phi xi and phi x and we know b, we can get the y hat for the test data from this equation. This is the decision function for nonlinear SVR. The method of calculating b is also the same as that of linear SVR. We'll look at this process in more detail later in the code that implements a nonlinear SVR. This is the decision function expressed as a kernel function. I referred to this article. Now, to solve this optimization problem, let's convert the dual function to the standard form of QP. Maximizing the dual function is equivalent to minimizing the negative dual function. The standard form of QP is as follows. As we did for support vector classification, we define the matrices as follows. The dot product of phi xi and phi xj is defined by matrix K. and the alpha is defined as the lambda matrix. This is an example where the number of data points is 2. And the remaining matrices are defined as follows. If you input these matrices into the standard form of QP, you can easily check that it is identical to the dual function above. Using this standard form of QP, the solution can be easily obtained with the CVXOPT library. Lambda and lambda star are the solutions to this problem. Next, let's implement a nonlinear SVR from scratch using CVXOPT. Let's write a Gaussian kernel function as follows. The formula is like this. The data we will use is like this. This is the data with noise added to a sine curve. We generated 200 pieces of this data. Epsilon, the error tolerance range, is set to 0.1. And the gamma of the Gaussian kernel is set to 5.0. And the regularization constant is set to 1.0. N is the number of data points. Let's use quadratic programming to find lambda and lambda star, the solutions of the dual function. To express the dual function in the standard form of QP, we construct the matrices as follows. Then input these matrices into the QP function of CVXOPT solvers and perform QP. The solutions to this problem are contained in this variable. Lambda and lambda star are the solutions to our dual problem. Now let's find B. Find the data x and y that satisfy this condition, and use this formula to calculate the dot product of w and phi x. Xi are the entire training data points, and x are the data points that satisfy this condition. And calculate B using this formula. Then find the data that satisfies this condition. Find Wx in the same way as above. And then calculate B using this formula. Then we calculate the average of B, and this is the final B. The data points with lambda and lambda star greater than 0 are support vectors. Finally, we visualize the data, decision function, and support vectors. Generate the test data like this, and use this formula to calculate the decision function values for this test data. This is the estimated curve for the test data. We also use this formula here to find Wx. X is the test data. Let's take a look at the results. This is the result when epsilon, the error tolerance range, is set to 1.0. All red data points are support vectors. The lambdas of the support vectors are all greater than 0. And the red curve in the middle is an estimate of the target value for this test data. It's drawing a smooth sine curve. And you can see the positive and negative boundaries above and below the sine curve. This is the result of setting the epsilon slightly higher to 2.0. There are 3 support vectors. You can see that as the epsilon increases, the regression curve becomes slightly flat like this. Next, let's estimate the regression curve using Scikit-Learn's SVR. Create a SVR model. Specify the kernel as RBF Gaussian. Specify the gamma of the Gaussian function. And specify the regularization constant C. And specify the epsilon, which is the error tolerance range. Fit this model to the training data. B can be found this way. This variable contains the lambda and lambda star values of the support vectors. and this variable contains the index of the support vectors. Now let's visualize the data, decision function, and support vectors. The results are as follows. These results are the same as the CVXOPT results on the previous page. When epsilon is 1.0, the results are the same as before. And when epsilon is 2.0, the results are also the same as before. Let's run this code. The results are as follows. This is the result of CVXOPT. And this is the result of SVR. Both results are the same. Let's check the results when we set the epsilon to 2.0. You can see that the regression curve is slightly flatter. So far, we have looked at the support vector machine through 10 videos.